In the last tutorial, we looked at the mechanics of fitting linear mixed effects models. And we also saw that there's a variety of different models that we can fit to a dataset. For example, we can choose to fit a model with random intercepts only, or a model with one or more random slopes. Equally, we can choose to include one or more than one fixed variables in our model as well. So clearly there's a variety of different models we can fit, which gives us, as the analyst, a choice to make about which model best represents our data. And in this next tutorial, we're going to be looking at the issue of model selection. That is the question of which of these various competing models provides the best representation of our dataset. So model selection is really the process of trying to find one single model that strikes the best balance between fit and complexity. If we make our model more complex by adding additional predictor variables or terms into the model, then those successively more complex models will provide a progressively greater fit to the data, and the R-squared metric, which measures the proportion of the total variance in the data that's explained by our model, will also continue to increase, albeit at a plateauing rate. However, more complex models are not always better. It's entirely possible that we can over-parameterize our model by having too many terms in it. This makes the model more difficult to interpret, and also reduces the ability of a model to make predictions for new conditions. This is illustrated in the diagram that you can see in the slide here. The three different plots show this identical data set where we're trying to describe a relationship between a predictor variable and the response. And we have models of three different levels of complexity. On the left, we have a very simple model. This is the simplest model you could get. It's a simple straight line which has a single degree of freedom. And clearly that very simple model provides a poor representation of the data. So we have a low fit to the data. It's simple, but poor fit. We call this model underfitted. On the right-hand side, we have the opposite problem. We have a model with 10 degrees of freedom. The model now has a lot of flexibility to describe the pattern in our data. However, as well as describing the overall pattern in the data, you can see it's actually also starting to describe the noise within the data set as well. In fact, this is a perfectly fitted model. It describes every single bump and wrinkle of variation in our data set. In this situation, we have a model which is overfitted. Although it provides a perfect representation of our data, it won't perform satisfactorily if we want to then make predictions for a new data set. So what we're looking for is a trade-off between these two extremes, which is what's shown in the middle diagram. Here we have a model of intermediate complexity, which does a good job of describing the overall relationship in our data, but doesn't overdo it. This model, which has this sort of optimum balance or trade-off, we refer to as being a parsimonious model. It provides a good fit to the data, but is no more complex than it needs to be. A parsimonious model, as I said, is both easier to interpret because it doesn't have too many parameters for us to look at, and also it should maximize the predictive performance, i.e. it will be the model which performs best when we try to predict the response variable at new places or new times. A number of different strategies that we can use to try and identify a parsimonious model. The whole topic of model selection is quite vast and can get quite complicated. So here I've attempted to boil it down by highlighting three commonly used strategies. There's obviously a lot of detail behind this, so if you're interested in getting into this topic in more detail, then I would encourage you to sort of go away and find some resources which will give you further insights into these different methods. Starting off at the top then, we have a stepwise selection approach. This is quite simple in essence. We start off either with a very simple model and then progressively add terms to it, or we start off with a very complex model which has all the predictive variables in it, and we progressively delete terms from the model. This is a search strategy which we refer to either as forward selection or backward selection, depending on whether we're making the model more or less complex as we go. And at each step, we compare the pair of models to see whether or not the addition or deletion of a term improves the model. We can do this either using a statistical test like a likelihood ratio test, which essentially asks whether the addition or deletion of the term explains a significant proportion of the variation of the data. Or we can use a metric called an information criterion, which provides a measure of the overall fit of a model, but includes a penalty for model complexity. So an information criterion essentially is a metric which tries to get straight to the heart of that complexity fit trade-off. Stepwise selection methods are good if we want to try and identify a model which is relatively simple and easy to interpret. They tend to be relatively good at penalising complexity in models. So variables which explain little or no variation in the response will tend to be weeded out, and we'll be left with a model which contains only the most important predictor variables. There are various different packages and functions available for implementing a stepwise selection process. The LMER test package includes a function called step, which implements both forwards and backwards selection using likelihood ratio tests to judge whether at each step in the process we have arrived at a better model. Alternatively, you can use the step CAIC function from the CAIC form package to perform stepwise selection using an information criterion called Akaiki's information criterion. That's AIC. This, as I said, provides an alternative to likelihood ratio tests, which provide a more direct measure of the parsimony of the model. The downside of stepwise selection is that if you were to take the same data set and apply both a forwards and backwards selection process to it, there is a risk that those two different search strategies may not necessarily arrive at the same answer or result. Also, the process of undertaking that stepwise search can be somewhat slow and cumbersome. A second approach that we can use is called multi-model inference. This is essentially a brute force approach, whereby we seek to fit all possible models to our data set. That large set of models features models which have all different permutations or combinations of different predictor variables. Having fitted all the possible models that we could to that data set, we can then rank the models using a metric such as AIC that identifies which of these many models provides the overall best representation of our data. And then rather than focusing on just the single best model, we can take a weighted average of, say, the top 5 or top 10 models and average the coefficient estimates and the predictions. That provides a much more robust way of quantifying the strength of effect of each predictor and also gives us more robust predictions. This approach is particularly useful if we want to judge which variables are most important. The variables which have the greatest influence on the response variable will tend to float to the top and will be present in the best models that we fitted. Equally, a predictor variable which is relatively unimportant will feature much less commonly in that top slice of best models. Multi-model inference also gives us an insight into the additional uncertainty that arises from the model selection process. And by averaging results across a small set of best models rather than focusing on identifying a single best model, then that gives us a way of averaging out some of that model selection error. One of the most widely used packages for implementing multi-model inference is the Moomin package. That features a variety of functions, including the dredge function, which can be used to fit multiple models to the same dataset. The downside of this approach, as you might imagine, is that it can be quite slow. It's a brute force approach, which relies on fitting a very large suite of models, and for very complex models and large datasets, that can be a slow process, albeit one that can be readily automated. A third strategy that we can use is one called cross-validation. Cross-validation involves splitting our data set into two segments. One of those segments is we call our training data set, and it's that which we use to train or calibrate our model. And then having fitted the model, we then apply that model to the other segment, the test data set. And this provides a direct way of measuring how well our model is able to predict the response under a new data set. Cross-validation is particularly good if we're focusing on trying to maximize the predictive performance of the model. It's not quite as harsh as stepwise selection at weeding out variables, so you may find that cross-validation does still tend to leave you with a relatively complex model, but it is guaranteed to find the model with the best predictive performance. When we looked to see what functions were available for implementing cross-validation, we found many, but none which were specifically designed for use with mixed effects models. So to rectify that, we developed a couple of bespoke functions, which are now included in the HE toolkit, which implement two different flavors of cross-validation for mixed effects models. Before we look at those functions, let's have a little bit of a closer look at exactly how cross-validation works. As I said, it's a resampling procedure we use to evaluate a model's predictive performance. So we're not only striving to find a model which fits our dataset, but also can give us the best possible predictions of how the response might, what values the response might take at either new locations or new times. And particularly if we're seeking to develop a hydro-ecological model where we want to simulate future scenarios, for example, or to extrapolate that model to predict the ecological response at new locations, then it's predictive performance that we're primarily interested in. The way cross-validation works, as I said, is to split the data into several different groups or segments. The way we do this is to split it into a number of what we call folds. Each of these, one of these folds is then emitted and becomes our test data set, and then the model is fitted to the data for the remaining folds. In the diagram you can see on screen here, we've chosen to split the data into 5 folds. The grey box on the right hand side becomes our test data set, and the 4 blue boxes are the training data set we actually fit the model to. We then repeat this process excluding or setting aside a different fold to be the test data set. So in the second iteration, it's the 4th fold that becomes the test data set, then the 3rd fold, the 2nd fold, and the 1st fold. In this way, we fit the model to different segments of the data and then have the ability to predict the response for the test data set. And by comparing the predictions to the actual measured values, then that gives us a way of quantifying how close the model's predictions are to the true values. To quantify the predictive performance, we calculate something called the RMSE, which stands for root mean square error. Essentially, that involves taking the predicted values for every observation in our data set and measuring how different they are from the true values. Those differences or errors are then squared, averaged, and square rooted, and that gives us a root mean square error. Smaller values of RMSE are better. Smaller values indicate that we have a smaller error or difference between our predictions and our true values, and so a small RMSE indicates a model with better predictive performance. Optionally, we can repeat this whole cross-validation process a number of times. Obviously, that carries an additional computational cost, but it also means that we get more precise estimates of the RMSE and therefore a better indication of exactly which model gives best predictive performance. The RMSE value that we calculate for each model can be then used to calculate different competing models and can also be used to guide a stepwise model selection process if we wish. As I mentioned, we've developed 2 functions in the HE toolkit for implementing cross-validation on mixed effects models. These functions are called model CV and model leave one group out CV. Let's look at those two in turn. They work in a very similar way but have very subtle differences which makes them suitable for different applications. Model CV implements the repeated stratified k-fold cross-validation approach. This means that we take our full data set with observations across multiple monitoring sites or locations, and the observations for each site are split as evenly as possible into k folds. Typically, we choose a value of k equals 5 or k equals 10, as that has been shown repeatedly to provide a robust measure of predictive performance. It's called a stratified approach because we're randomly splitting the observations within each site, and that guarantees that each of the folds contains at least one observation from each site in our data set. We can, if we wish, repeat that process a number of times, which is controlled by the R parameter. The RMSE that we calculate using this method quantifies the model's ability to predict the response for new samples at existing sites. So if the aim of our analysis is to make, for example, future predictions for the sites in our calibration data set, then the model CV function is an appropriate way of comparing competing models. And it in particular puts more emphasis on the variables in the model which explain the temporal variation, the variation in the response over time at each site. You can see on the slide here we've got some example code just to illustrate how that function works. The arguments to the model CV function include, first and foremost, the model that we've fitted to the full data set. We also feed it the data set that we've used to calibrate that full model. We then identify which variable is the grouping variable, so that would be our biology site ID, and then we set the K and R parameters. As I said, K equals 5 is a commonly used and a suitable value to use, and you can choose how many repeats you want. Again, in my experience, have it setting R to repeat the whole process 10 times usually yields pretty robust estimates of RMSE. When we run the function, we save that as an object, which we've called CV, and that is actually provides us a list of two outputs. The first element of that list is the RMSE estimate itself. So in this example, we get an RMSE of 0.0338. That is a measure of how close the predictions from the model are to the true values when we try to predict for new samples at existing sites. The second part of our output is a table, which you can see illustrated in the middle of the slide, which for every observation in our data set gives us both the true value of the response variable and also the cross-validated prediction. This allows us to see whether there are any individual observations in our data set which the model is particularly poor at predicting. The second function that you can use in the HE2 toolkit is the leave one group out cross-validation function. As the name suggests, this works in a slightly different way. Rather than stratifying the cross-validation process by site, we simply leave out one whole site from our dataset each time. This essentially means that the number of folds, k, is equal to the number of sites. So in essence, we take our complete dataset, remove one site, fit the model to all of the remaining sites, and then use that model to predict the response for the individual site that we excluded. And then we repeat that process for every site in our dataset. In this way, we are able to calculate an RMSE that quantifies the ability of the model to predict the response at new sites. So if we want to calibrate a model to the sites where we have monitoring data, but then subsequently wish to use that model to predict the response at new unmonitored locations, then the leave one group out cross-validation approach is the right one to use. Because of the way it works, it also tends to, in contrast to the model CV function, it tends to put more emphasis on variables which explain spatial variation in the data. Again, you can see on the slide here some example code. It works in a very similar way to the model CV function. We set the model argument to be the full model that's fitted to the complete data set. We also give it the full calibration data set and define the grouping variable that we wish to use. Again, the output is a list containing firstly the RMSE value and secondly a table of cross-validated predictions. As you can see here, if you compare the RMSE values using these two different functions, you'll see that typically the RMSE is greater when we use the leave one group out cross-validation approach than it is when we use the standard stratified cross-validation approach. This is because typically it's harder to predict the response for a completely new site than it is to predict the response for a new sample at an existing site. So developing models which we can extrapolate spatially tends to be a little bit more difficult than developing models which allow us to predict the value of the response under new times at an existing site. Both of these functions can be used to either compare competing models or can be used as part of a stepwise selection process to determine which variables should be added or dropped from our model. Model selection is one of the slightly more complicated and time-consuming parts of the whole hydroecological modelling process. So on this slide, we've just set out a few sort of tips and bits of advice which we have learnt from experience over the years of applying these models. The first thing to say is that when we're dealing with mixed effects models, it's useful, I think, to start off by focusing on the fixed effects first, deciding whether or not we want random slopes, and if so, how many, and having then determined what the random effects structure of our model looks like, we can then, as a secondary step, move on to do model selection on the fixed effects. When it comes to the random effects, first and foremost, we should ensure that we always have a random intercept in the model. This is important to account for the hierarchical data structure. The fact we have samples nested within sites means that we have to account for that spatial structure in our data. If we fail to do that, then we commit to what's called pseudo-replication, which results in artificially optimistic looking p-values and gives us false positive results. As we saw earlier when we were looking at the mechanics of fitting these models, there is a practical limit to how many random terms can be included in a model. Trying to force too many random slopes into a model will result in singularity or the model failing to fit altogether. Because mixed effects models are very efficient at accounting for random variation from site to site, there's actually limited benefit in from a practical point of view of trying to have a parsimonious model. And there is a school of thought that you should try to choose your random intercepts and slopes based on the aims and understandings of the data. That said, there will be a practical limit, and if your model is too complex for the amount of data you've got, you will hit model fitting issues. We also looked at the problem of singularity, which occurs when the model is potentially too complex for our data. Singularity can arise in two ways, either when some of the random variances approach zero, or when we have high covariances between the random intercepts and slopes. Zero variances tend not to be too much of a problem when it comes to model selection. If a particular random term has a zero variance, then it's going to be having no effect or contribution to the model whatsoever. However, high covariances, where the intercepts and the slopes are strongly positively or negatively correlated, can be more the grounds for concern. And in that situation, we may wish to consider simplifying our model by dropping some of the random slope terms. Having got the random effects as we want them to reflect the hypotheses that we're testing, and also to make sure that they're no more complex than can be supported by the data, then we can turn our attention next to the fixed effects. We can have any number of fixed effects in the model, and those can be continuous or categorical variables. The most important thing is to ensure that we avoid including in the model any variables which are very highly correlated. High collinearity means that those different variables which will be hard to distinguish their independent effect. Variables which are very strongly positively correlated will tend to have negatively correlated coefficients, and those coefficients will have inflated standard errors as well. This means we reduce the ability of the model to distinguish the exact effects of those variables, and that in turn can also lead to reduced power to detect statistically significant effects. As a rough guide, any pair of continuous predictor variables which have a correlation coefficient of more than 0.7 are potentially too strongly correlated. An even better test of collinearity is to calculate what's called a variance inflation factor. This can be performed after fitting a model and will identify any variables which have high collinearity with other variables in the model. And as a rough guide, any variable which has a variance inflation factor greater than 3 should potentially be dropped from the model. We should also be wary of including too many fixed effects in the model. Those fixed effects can be both main effects and interactions. Where possible, we should try to include variables based upon an a priori hypothesis that we want to test. If we don't do that, and we just include all the variables that we could possibly find and throw them all into the mix, then we go on a bit of a fishing expedition. If you put in 20 variables, then just by chance, at least one of those will show a statistically significant effect on the response, but that may be entirely spurious. And so to guard against those false positives, we should be much more selective about which fixed effects we choose to include in the model. Finally, just a reminder that although we can calculate p-values for the fixed effects in the model using the LMER test package, those p-values are very approximate, and we should not use those to guide the model selection process. As we looked at earlier in this tutorial, there's a variety of different methods that we can use for model selection, and if you do want to use stepwise selection, then there are better alternatives than using p-values. You can use likelihood ratio tests, or you can use information criteria. Hopefully that's given you a few practical tips to help you decide what the optimal parsimonious model is for your data set.